All right, let's dive into something that feels like science fiction, but is happening right now all around us. We're going to talk about computer vision and really break down how we're teaching machines to do something that we do without even thinking, the absolutely incredible act of seeing.
So let's just start with the central challenge, the big question right at the heart of it all. You and I, we can glance at a friend, a car, or, a piece of fruit and instantly know what it is. But for a computer, it's all just a giant sea of data. So how in the world do we bridge that gap? Well, to find the answer, we first need to understand the gold standard we're aiming for. Yeah, to really appreciate how tough this is, we have to start with the benchmark we're trying to hit, our own vision. It's something we do so effortlessly every single second we're awake, but the processing power it requires is, well, it's nothing short of miraculous. I mean, just think about this for a second. This fact is staggering. A full 50% of your brain is dedicated, either directly or indirectly, to processing visual information. Half of our brain power is just for seeing. That's a huge amount of biological hardware.
And it's not just powerful. It is unbelievably fast. Your brain can correctly identify an image you've seen for as little as 13 milliseconds. That's faster than a single frame in a movie. It happens before you're even consciously aware of what you've just looked at. Just incredible.
Our visual memory is just as impressive. Studies show that people can remember over 2,000 different pictures with at least 90% accuracy. Our brains are basically natural high-speed archives for the visual world. So yeah, this is the amazing benchmark we're trying to replicate in machines.
And that brings us to this quote, which I think perfectly illustrates the goal here. See, computer vision isn't just about putting a camera on something. It's an information processing task. It's about teaching a machine to not just look at the visual world, but to understand it, to find the actual story behind the picture. Okay, so how does the machine even begin to see? What's the very first step? Well, it's something called image acquisition. It's the process of turning the physical world of light and shadow into digital information a computer can actually work with.
As you can see, it's really a four-step journey. It all starts with a light source, like the sun, which lights up a scene. Then an imaging system, a camera, captures that reflected light. That light gets projected onto a sensor, and finally, it's converted into what the computer understands, a digital image.
Now here's what's so fascinating. What is that digital image really to the computer? It doesn't see a picture of a cat. It sees a mathematical function. It's just a massive grid of numbers where each number represents the light intensity at one specific point. We call those little points pixels.
To create this grid of pixels, two key things have to happen. First, you've got sampling, which basically figures out where on the grid each pixel goes. Then you've got quantization, which decides what value each of those pixels gets, its specific shade of gray or its exact color. Together, these two steps turn our smooth, analog world into discrete, digital data.
And here's how that data actually gets stored. For a simple black and white or grayscale image, it's just one number for every pixel. For a standard color picture, it's 3 numbers, representing the intensity of red, green, and blue. In that combination, it allows for a mind-boggling 16.7 million different colors for every single pixel.
Okay, so now the computer has the image as this huge grid of numbers. But raw data is rarely perfect, right? So the next crucial stage is what we call low-level processing, which is all about cleaning up that data and getting it ready for some real analysis.
Think about a photo you've taken in a dark room, or one that's just a little bit blurry. The information is there, but it's kind of hard to make out. Well, a computer faces the exact same problem. It needs to enhance that image to pull out the useful information that's hiding inside.
One really powerful way to do this is a technique called histogram equalization. The best way to think about it is like turning up the contrast on your TV. The process takes all the pixel values that are bunched up together, like in an image that's too dark, and it spreads them out across the entire available range, from the absolute darkest dark to the brightest bright.
And the result of that? It's a huge increase in contrast. All of a sudden, details that were once hidden in the shadows or washed out in bright spots just pop. This isn't just about making the picture look prettier for us. It's about making the crucial information inside it way, way easier for the computer to find.
Now this is where things get really exciting. We've captured the image, we've cleaned it up. Now we're ready to move from just processing pixels to actually understanding what those pixels represent. We're moving from data to meaning.
It's really important to see that there are two levels to this process. You've got low-level vision, which deals with the raw data. It asks simple questions like, what color is this pixel? But high-level vision, that's the ultimate goal. It asks, what do all these pixels represent? It's about interpreting the data to identify objects and understand the entire scene.
So how does a computer build this understanding? Honestly, it's a lot like building with Legos. It starts with the simplest little pieces. It finds edges where brightness changes really sharply. It looks for simple shapes, like lines and corners. And then it starts grouping all of these simple features together, combining them to recognize bigger, more complex objects, just like building a house from individual bricks.
And this is the magic moment. After all that processing, a super complex visual scene, represented by millions and millions of numbers, is boiled down into a simple, symbolic description. The computer doesn't just see pixels anymore, it sees a bowl of fruit.
So now that we've seen how it works under the hood, let's zoom out a bit. Why does any of this matter? Why is teaching computers to see so incredibly important? Well, it's because the applications are already transforming our world.
Computer vision is the core technology that lets self-driving cars detect pedestrians. It's what's behind the face recognition that unlocks your phone. It helps doctors analyze medical scans to spot diseases earlier than ever before, and it's used to build these incredibly detailed 3D models from just a few regular photographs. It's everywhere.
But, and this is a big but, for all this progress, we have to remember that vision is still a really, really hard problem. The same exact object can look completely different depending on the viewing angle, the lighting, its size, or if it's partially hidden. These are the huge challenges that researchers are still tackling every single day. And this quote just captures the state of the field perfectly. Trying to emulate human sight is an immense challenge, but the progress we've made has been nothing short of explosive, and we're getting closer and closer every single day.
And so we end with a final, and I think crucial question. As we give machines this powerful, almost human-like ability to see our world, how is that going to change the way our world sees them? What does a future look like when the world is not just seen by us, but also understood by the very machines that we've built?